In this lecture, we will simulate the electric field around the microstrip line and show how the electric field strength is better contained when the PCB thickness gets reduced. For beginners, microstrip might be a confusing term, but just think of it this way. Every single trace on a PCB that is placed above the ground plane will basically behave as a microstrip. So all your traces on the top layer of a PCB will have a better contained electric field if the ground plane below the trace is closer to it, which means that we prefer a thin PCB. In general, on the bottom side, a microstrip is contained by the ground plane, but on the top side, the field will extend forever. The only way to shield a microstrip's electric field is to place a shield can above it. As you see, the shield can helped, but it seems that there are still some field lines extending out of the PCB material. You can only shield the field lines if you add vias all around the PCB. This now looks good on our two-dimensional simulation. But looking at the problem in 3 dimensions, you would find out that there are still fields escaping through the slots between the vias. So the standard way of manufacturing a PCB cannot fully contain the electric fields. But there is a production process called edge plating or side plating, which will cover the sides of the PCB with full copper. The PCB will look like this after using this production process. Open FEMM 4.2, create a new project, select electrostatics problem, and click OK. Save the project. Click on Grid, and then click on Snap on Grid. Let's now set the grid. I will set it to 5. We want to draw following setup. If you know how to draw this by yourself via FEMM 4.2, you can fast forward this part of the video. I will start by placing the point segments. Let's place the first point into the center. The second point is 35 above. I will later set the problem parameters to 35 micrometers, hence 35 means 35 micrometers. Let's place another 2 points, 200 micrometers to the right. Select the line segment tool, and let's connect the 4 points with the line segments. We will end up with our trace, which is 0.2 millimeters wide and 35 micrometers thick. Now select the block label and place it into the trace. We will set the inner part of the trace to no mesh instead of setting it to copper. This is because we will only set the surface of the trace to a potential. As the problem is static, we can ignore that there is copper inside the surfaces of the trace. Now go to Properties and Materials, add one property and set it to Air. Now right-click in an empty space around the trace and place the block label here. Right-click on it, hit the spacebar on the keyboard to open the property window. Select Air. Now we will create 2 more boundaries for the ground voltage. The 1 volt boundary I will simply call 1 volt. Select the line segment tool and mark all the 4 lines of the trace. You can mark multiple lines by holding Ctrl on the keyboard and right-clicking on the lines. Hit space and set them to 1 volt. Before creating the 0 volts boundary, let's first draw the points for it. Place 1 point at x equals minus 2000 micrometers and y equals 0 micrometers. You can zoom in and out with these buttons. Moving left, right, up and down can be done with these buttons. If you want to extend to all drawn components, click on this button. Zooming into a specific area can be done via this button. Let's connect the lines with the line tool. As we want to draw a 1.6 mm thick PCB, the next 2 points are minus 1600 micrometers in y direction. Let's again connect all the lines. Now place two further points 35 micrometers below and connect them again. Create another boundary for our ground potential or 0 volt potential. Mark the ground plane's line segments by right-clicking on all of them while holding down the Control key on the keyboard. Hit space to open the property menu. I will now place 2 points for the infinity boundary in some distance to the PCB. 5 mm to the left and the right will be enough. As the PCB is 1600 micrometers thick, y equals minus 800 is simply the center of the PCB. You can draw a circle on the bottom side of the points by clicking on the left point first and then the right point. Now set the angle to 180 and the boundary condition to 0 volts. The top side circle is drawn by first clicking on the right point and then on the left point. Set this one also to 0 volts. Let's now place a block label inside the lower copper area. And set it to no mesh. Place another block label inside the PCB area. We will set the material to FR4. For this, go to Properties and Materials. Call it FR4 and set the relative permittivity to 4. Right-click on the block label and hit space on your keyboard. Set the block type to FR4 and click OK. Now let's draw the mesh and run the solver. Switch to the Results tab by clicking here. Click here to change the view to Field Intensity. I will adjust the top limit to 1600 and the bottom limit to 10% of that. There is not much more to see now. This is because the field strength is mostly concentrated on the edges of the top trace. Let's change the limits to 160 and 1600. Now we will see more of the field strength distribution. As you see, the field is the strongest right around the upper trace. It extends from the upper trace in a circular shape. Also, there is a position in between the trace and the ground plane where the field strength gets weaker. Now let's open another FEMM window. For this, just create a copy of the project file. The overall layout will be similar to the previous one. We only need to move the ground plane 1 mm upwards to end up with a PCB thickness of 600 micrometers. Create the mesh, run the solver, and switch to the Results tab. I will now place the results of the two simulations side by side and display the field intensity on both. As you see, the electric field on the 0.6 mm thick PCB is better contained. This three-dimensional case, check out my course on 3D FEMM simulation with KiCad.